Okay, guys, can you hear me again? So the next thing, or the last thing that I wanted to do is talk a little bit about copulars, and I should be down here now. How can we use, how do we model defaults? We started talking about that last time when we did the CDS contract. So let's just recall. Let's recall the default model from last time. This is when we did the CDS contract. So you say you have a diffusion. We call it Y, I think. So dyt would be some drift and some volatility, and then you would have a function lambda. And what will be important here, so yt, let's just say that this is one-dimensional, and so lambda goes from R, and then it takes positive values. So this is a function, right? And then you construct the default time. The default time is constructed as the first time. So that's what we denote by inf. That the first time, the first time that, say, the integral from 0 to t, and then you put a minus there, and then it's lambda y of u du. The first time that this gets to be equal to capital U, like where u is going to be independent of y, and u is uniform on these intervals 0, 1. So what is happening is that lambda is positive, and so when you integrate over larger and larger areas, you're going to get something here that is more and more negative, right? So this here is a decreasing process. This here, this is a non-increasing process. That's because lambda is positive, right? Lambda is positive. So on a picture, where we have timeout here, what happens is that you pull a uniform. This here is 1, right? So you're going to pull a uniform. Say it ends up being there. That's my u, so we're going to mark that. And then you plot this object here. When t is equal to 0, you get e of 0, that's a 1. So it starts here, and then it's a non-increasing process, and it goes down, it's random. It could be flat somewhere, you go down, and then when it hits the level u, this is where tau comes into play. The path you see here, this is my attempt of illustrating a path of this exponential of y. So this is a famous way of generating these default times. This is called the Cox model. Right, and so let's just think for a second about what we did last time with the CDS contract. Right? So CDS, so the CDS pays 1 minus pi at the time at time of default, right? So this is at time tau. If tau is a tau of omega, tau of omega is less than say 1 year. So this is a 1 year CDS. Could be other maturities, but let's just do a 1 year. It pays 1 minus pi. This is for all practical purposes. This is 0.6. At time of default, if default happens within the first year, right? So there's a 1 year window. There's a 1 year window, and so it might very well be that this process here never gets below u within that 1 year window. In that case, the CDS pays out nothing. Otherwise, pays out 0. So, and then there's a fee, right? You're buying this protection, so you're paying a fee. So you can pay all up front, or you can pay running. You can pay till default, or expiry of time 1, whichever comes first. And so we have the 2 legs, and we match the legs, and this is what we get for the fair. This is how we determine what the fair fee is. Actually, the fair fee is this is called the spread, is set such that both legs have the same value at time 0. So we looked at an example last time. So what I want to do today is move a little bit beyond that. I want to look at a contract that has a more complicated structure. And we looked at last time how one can simulate this, and it's not too tricky. You simulate y, and then given the path of y, you can transform the path of y into this thing that decreases, and then you just check for default. To talk about copulars, what so why would you want to have copulars? Well, so copulars. This has to do with multiple firms. Firms are also called names. So you would have if you say we have 2. Oh, there's another mosquito in here. Got him. What you'll have is, if you have 2 names, so this here could be firm 1, and this one here could be firm 2. You want to use exactly this model here for each of the 2 firms. So then what you do is you look at a picture. So you'll have firm number 1, he has a U1 of omega. So this is 1. And firm number 2, he also has a uniform. This could be U2. These are random and they're uniform. And you draw the picture. And when it hits, this is when firm number 1 defaults. And this process here, this is e to the minus an integral from 0 to t. And then is lambda 1 applied to y. Y is the same for both firms. And up here, you can see U2 is much higher. So firm number 2 defaults quickly. And so in here, you would again have the exponential function, but instead of a lambda1, you would have a lambda2 of y du. So you have a Cox model for each firm. Now the tricky part here is these u's. So the tricky part, and this is where the copulars come in, the tricky part is for the tricky part, and this is where the copular comes in, is modeling the dependence between U1 and U2. Right? Each U UI is uniform, but you're not independent. But not independent in general. So this is what copulars is all about. It is to allow us to model this joint, the joint distribution of two uniforms. So the definition of a copular, so a function, so a distribution function, say f, it goes from 0, 1, and so I is up here. This is the number of names. Number of names. Distribution function, and then it takes positive values. A distribution function is called a copular if it has a uniform marginals. I shouldn't call this F, I should call this for C. So what it means is, so to be a distribution function, so in 2D, so if I say that I is equal to 2, if I is equal to 2, right, then I would have, if I look at a little square here, so this here's my A, this here's my B, and let's do a C, let's do a D, right? So if I'm looking at, if I'm looking at the probability that U1 is between A and B, and U2 is between C and D, right? So we have a 1 out here. We have a 1 out here. So I want this to be positive. So how would I calculate this joint probability using the distribution function? Well, I would say, what would I say? I would say, but look at C evaluated at BD. That's going to give me everything that's underneath it. That's too much. So I would subtract away, BC. And I would subtract away AD. And then I subtract away, I subtracted this square down here twice, so I need to add that back up. right? So to be a distribution function, I need something like this to be positive. Like not all functions are distribution functions, so I need this to be positive. And to be a uniform marginal, so that has to do with being a distribution. And if I want to have a uniform marginal, I need to have that U is the same thing as the probability of U. So here it's downstairs. You have it upstairs or downstairs. I think I want to have all the indices downstairs. So let me move the indices up here from upstairs to downstairs. Right. So if I want to have uniform marginals, I need to have that the probability that U2 is less than U and U1 is less than U. I need these just to be U. And if I want to express this in terms of the copular, in terms of the joint distribution, this will be C of U and then a 1, right? Because here we're just going to have that U2 is less than 1. And likewise over here, this is going to be C of 1 and then U. And that's what it means to be uniform. So these are properties that I have, but there are lots of copulars out here. So the uniforms are marginal, and what the copular does is it tells us what the joint distribution is. And okay, so that's what I want to spend the last of today's lecture talking about these copulars, what you can get out of them. Why would one want to study stuff like this? So one reason for studying copulars and these models will be the n to default contract. And these are like precursors. These are like early or simple versions of what became known as CDO contracts. CDO, I can't spell it. It stands for collateralized debt obligations. CDO, there's also a mortgage version. There's also a credit card version. CDO, CMO contracts. The nth default contract, it works very much like a CDS. So here you place, so this is called n to default. So you place a bet. You place a bet on a pool of names. Say in my numerical example, we're going to look at it in a second, they're going to be 5. You place a bet on a pool of names, say 5, and and depending on the size, if you're long or short, and you pay, you get paid if and when firm N defaults. And you get paid, this is the same thing, you get paid is 1 minus pi. Right, so you have, say, 5 names, and you're betting on like that there will be a second default. So if n is equal to 2, you're betting on the second default. So in return, you pay a fee. You pay a fee till the second default. Till till the nth default, or time expires as before. So if you're betting on, if you're looking at the first to default, has to happens before the second to default, and so on. Right. So the fees that you're paying, they of course reflect how likely it is that you get the price, the 1 minus pi, which again, think about this as being 0.6. You put $1 in the notional, then you're going to get paid 60 cents if and when firm number n defaults. In return, you're paying a fee all the way up to that time, or time 1 when the contract expires. So if you go back to the picture, we now have our two firms. So if you only have two firms and they look like this, well, then you can see in this model, like the first to default is going to be firm 2, and the second to default is going to be firm 1. But when you place the bet, you're not betting on an individual firm, you're just betting on the number that will default. You don't care if it's firm 1 or firm 2. These contracts, when they were traded, they typically had 12 to 15 names in them. The CDOs that I mentioned at some point, they had many more. And so there's a slightly different structure. The CDOs and CMOs, in particular with the mortgages, there could be thousands of names in there. So this here is like a quite easy compared to these more general structures, and they carry a lot of the same similarities. So that's why I'm just talking about them. Does that make sense? We have a first to default, and we have a second to default, and a third to default, and so on. So let me, before we do math, let me just show you how it looks like, how the code would look like, how my code would look like when I coded it up. So see, lecture number nth to default. That's this one here. Okay, so we have in this particular case the time horizon, I put it to be 5 years. There's an interest rate. There is a pi is not 0.4 but 0.35, and then there's a row, and this is what is coming up next. There's a parameter row in here, and that row is what's going to determine the dependency between U1 and U2. Okay, so we will talk a lot more about that in a bit, but you can see the code here is not elaborate. It's what the code is like 40 lines. And all it does is that it keeps track of these default times. It just sorts them and looks at the first, the second, the third, the fourth, and the fifth. And then it computes the values of the two legs, and it equates them. Very similar to what we had done last time. So let me try to run it so you guys can see how it works, how fast it runs. Not particularly fast, but still. Here it spits out values. So keep in mind, it's a 5-year horizon, right? So it spits out what are the values of the two legs. This top part here, this is going to be the value of the recovery leg. So this is the phi 1 minus pi. In this case, pi was 0.36. So the value is 0.65. The phi leg, this is you pay. So you, what is the value of the phi leg? And you equate these two and you're going to get the spread. So the top part here is when you see the spread for the first to default contract. So this is, what is it, 444 basis point, like 4.5%. And then you can see it tapers off, and the fee for the last contract is it's out on the 5th digit. Now, what's interesting here is that this is correlation parameter, right? And the correlation parameter, this has to do with the normal distribution. So remember, we had talked about how to simulate joint normals. Remember, we had talked about that if you had a volatility matrix, so this is the variance covariance matrix, you have ones on a diagonal. And in this case, off the diagonal, I just have a constant rho. And here rho is 0.2. Then we can factor, we can generate, we can sample normals from this variance covariance matrix. And to do that, we need this Koleski factorization, which we're going to get a lower triangular structure, and we take independent normals and we multiply them onto this Koleski factorization, this square root process. This is what we were talking about, principal agent components some weeks ago. And then what we get is we get a bunch of jointly normals, and then we transform these normals to get uniforms. And the way that we do that is just transforming it by the standard normal distribution, right? So mean 0, variance 1, and you just transform these x's into uniforms. But now these uniforms, you have a special dependent structure that is coming from this volatility this variance covariance matrix up here, sigma. And the important part is when I start playing with this correlation, if I start playing with it, if I increase it to say 0.8, so we have a high correlation, well then these numbers really changed quite a bit. You can see when the correlation becomes higher, the first to default spread drops and the fifth to default spread increases. It becomes more similar. And indeed, if I go up to say 0.98, if I go up to 0.98, we're going to get very similar spreads. That means that as the correlation increases, these contracts, they're going to carry the same you're going to carry the same risk because you're paying the same price for them. And so when people talk about CDOs in the 2008 financial crisis, the model that everybody used is exactly this piece of code that you're seeing here on my screen. It's what's called the Gaussian copula. And it was modeled with this flat off the diagonal correlation matrix, one parameter. And then this rho would vary over time. And it was in general believed early on that this last contract, the fifth contract, the one that has this very teeny tiny spread here, this would be highly unlikely to ever happen. Right? What is the chance that we see 5 defaults? Apparently, it depends a lot on the correlation. If the correlation is high, seeing the fifth default is more or less as likely as seeing the first default. And this is where the breakdown happened, and these CDO contracts, they were so mispriced because people didn't believe that you could have that many defaults, right? So when you had a mortgage pool of 100,000 mortgages, what would be the chances that you would see more than 50,000 mortgages default? Well, if you have independence, it's a teeny tiny probability. But if you have perfect dependency, it's a huge probability. And so this has been floated or suggested as a possible cause of the financial crisis. So I'm not going to point fingers. I'm just here. All I'm saying is that the numbers we get out of our little model here, like it is a little model because it's just 40 lines on the left-hand side of my screen. What we see here is that it apparently depends a lot on the correlation. If the correlation changes, these numbers will change radically. Right, so when you estimate this parameter rho, that is quite important to get these spreads determined. Are there questions so far? other thing I wanted to show you is if you go to our Zoom, and not Zoom, if you go to our Canvas site and you pull that file, there's a file here called notes and copulars. This is from last time I taught the course. And if you flip down here, the model that we're working with is exactly this thing that we had talked about before, that you have a variance covariance matrix. That's your sigma. You factor it out into a square root, and then you take independent normals and you just multiply onto the square root. Then you're going to get joint normals. And if you have joint normals, we simulated them before, you can look at them. You can look at them. Of course, I can only plot in 2D here. So you're looking at x1 and x2, the two firm case. And here we're looking at them at the level of normals. But I can project these normals down into the interval 0 to 1. So this is what I'm seeing here, U1 and U2. Those are those thresholds that we had in the Cox model. Right? And here the independent. And the way that I transform them to get them to be uniformly distributed is nothing else. And I just plug them into the standard normal distribution function f. Here's denoted by f bar. Right, so I take my x that I get down from here, I plug it into f bar. This is going to give me a number between 0 and 1. And those are the numbers that I'm plotting here. Then we move on. We can now do the same thing, but instead of having uniforms, instead of having independence between the normals, we can put in a correlation parameter. So here I put in, I forget what it was, 0.8, I think. So we have now positively correlated normals. So you get something that looks like this on a diagonal. And again, I can transform them into uniforms by applying this the distribution function to each one of them, and I get numbers between 0 and 1. And you can see now there's clustering. There's clustering up at the upper tail, clustering down at the lower left quadrant. There's no activity up in the upper left and the lower right quadrant. And if I switch it around, or this was correlation 0.9, if I switch around and I get negatively correlated, then I'm gonna moving exactly on the up in the upper left and the lower right. And again, you plot them, convert them into uniforms, then you're gonna clustering up in these two ends. So I have heavy tail dependence here, and you might not like. This here was the standard copular model that people used to model these first default and to model these CDO contracts that we haven't talked about, but you're not that different than what the first and second and third and fourth and fifth default contracts were. But you could be interested in generating something like this. Again, you have uniforms, right? So you're between 0 and 1 and between 0 and 1, two firm case. And now you want to have like an upper tail dependence. And you could be interested in having something that had a lower tail dependence. So these distributions, they are different. So here you have the names Gumbel and Clayton. And let me show you how one can go about doing that. Here, not like the normals, this is a different distribution than the normal. Let me talk a little bit about a huge class of copulars that also got popular, but not as popular as the normal. Right, so let's just reiterate, like the normal copular samples. The way that you go about doing it is you write your sigma. This is your variance covariance matrix. Right, so this in our example, what that was, this was 1, and then it had row, and then it had row 1, row, and then it had 1 here, row everywhere else. Row was a positive number. Like being 0 is independent, being 1 is perfectly correlated. And then you'll factor out sigma into a into a variance covariance matrix square root. So you write this here as AAT. This is the Koleski. And then you sample, and then you set your x, simply as AC, where C is standard normal with independent increment. So here you have only, you have the mean. We'll be more careful here. Like the mean has zeros, and the variance is just 1, 0, 0, 1. So Z is standard normal with independent coordinates. You get the matrix A by factoring out in Koleski, and then you take A times C, then you're going to get X, and then X is going to be standard normal. Sorry, X is going to be normal would mean 0, and then the variance covariance matrix sigma. Right, so to get UIs, to get UI, you look at f of x. This is just a standard normal distribution, right? Inside sigma, each xi is standard normal. To get UI, you simply just transform with this function, the standard normal distribution function. You define this and use that xi is standard normal. Your x1 down to xi. This is what I mean by x. Xi is standard normal, means 0 variance 1. And you can see that inside here we have the means, they all have mean 0. The variance covariance matrix has ones on the diagonal, so that's this one we get here. Then your UI is simply just going to be f this distribution function composed with xi. So these are uniforms with a Gaussian dependence. Structure. Right, because they come from this xi, and the xi is the Gaussian, and it has this row correlation structure. Here we just projected them down into the UI. So when you go about sampling, you have to create these UIs to figure out when the thaws happen. And so you have to be able to simulate these U1, U2, U3, and so on. And the way you do it in a Gaussian copula is you simulate X by using this Koleski factorization thing that we talked about before. And then you just transform these normals by the standard normal distribution function, and you will get the UIs. And these UIs are not going to be uniform, and they're going to be dependent upon each other. Right, so U1 here is not going to be independent of U2 in such a model. Any questions on this part? So let me spend the last 15 minutes talking about these these models that will give us this upper tail dependence and lower tail dependence, and maybe look at a few pictures. So there's a class of copulars. There's a class of copulars called Archimedean copulars. Archimedean copulars. Okay, so they're parameterized in terms of a function phi. So you have a phi. It goes from 0 to 1 into 0 to infinity. And it starts out at infinity, and it ends up at the other endpoint, at the one being 0. And it's strictly decreasing and convex. Decreasing and convex. So on a picture, you have your phi. Here we have the 0.1. So inside here it blows up and it comes down to here. This is our phi. This is called a generator. So phi is called a generator. The copular corresponding to phi is given by, and there's a formula. So you're looking at, this is my distribution function with uniform marginals. This is u1 up to ui. This is defined as phi inverse applied to the sum of phi of ui, with ui's being between 0 and 1. And this is an Archimedean copular. So I should say here the Archimedean copular. Is it Archi? I think it's A-R-C-E. Yeah, I think it's A-R-C median. The Archimedean copular corresponding to such a function up here has this very simple form. And some examples that so some examples. Of course, the first one is make sure I'm not saying something silly. Yeah. So the first one would be say the Gumbel. Here you take phi of x, and phi of x is minus log of x to the power of theta. I think theta here is bigger than 1. So that would be one example. The other one that is often mentioned is called Clayton. The other one is Clayton. He takes phi of x to be x minus theta minus 1. I think this one here is taken to be bigger than 0. So we could also, when we describe the dependencies between all these individual uniforms, we could pull them from a copula in this family, in this Archimedean family. And for example, we could have these functions here. Now, one could then ask, so how complicated is that going to be? And let me just show you, we're running out of time, so I don't have that much time to show you all the details, but I can at least show you that it's not that complicated. I wrote a little piece of code here yesterday, and you can see how involved it is. It is really not involved at all. So I'm taking, I have two names, and I want to simulate 1,000 realizations of these uniforms. My theta, I took a P2, and here I'm looking at generating 1,000 samples of the Clayton copula. So there is a formula for doing this, and just to give you an idea about how much time it takes, run it, and there we have 1,000. Here we have 1,000 points from these coming out from the Clayton copula in 2 dimensions. And you can see there's a lot of activity down in the lower left corner. And then it spreads out. We have less activity in the upper left and lower right. And if I start playing with the theta parameter, so if I have a 2 here, if I increase it to a 5, we get a different picture. You can see it becomes more concentrated down in the lower left. And it shoots up in this cone. And I can do, instead of the Clayton, it is a small change to get the Gumbel simulated. So to get the Gumbel simulated, I'll run the code again, and now we're going to see this upper tail dependence. The theta parameter is 5, and there is some lower left tail dependence too, but it's mostly up in the upper right that we're going to get the action. And if I lower the theta parameters and say 2, we're going to get slightly less action up in the upper right. I know it spreads out more. Yeah, we're almost out of time. So looking at my code, you can see it only takes, I pull uniforms and then I do something to these uniforms. And you can see in here, there's something with that generator function that comes out. 3 lines and I can simulate these points. So it's not complicated to simulate from the Archimedean family. There's a trick in here. There's something called Marshall and Alkin's trick. Marshall and Alkin's trick allows us to fairly easy simulate the use with that correct dependency structure. I had hoped to go through it, but it's like 4 pages of notes to explain this, so I will have to do that next time. I'll have to do that next time we see each other. Are there any questions or comments about what we've been doing today? So once again, it is really time for you guys to pick a project. If you have questions about the project, you can use my office hours tomorrow. Otherwise, please pick a project. And what's going to happen is that there will only be, I think, there are 6 homeworks planned. So we've done 3, and number 4 has been posted. So it's also time to start thinking about the project and and ultimately you have to write a report. Are there any questions or comments before we call it quits? Okay, then next week is spring break. I do have office hours tomorrow from 9 to 10. Otherwise, if I don't see you, I will see you after spring break. Oh, there's somebody asking. No, I cannot hear you. In Young, I can't hear you. No. Yeah, just type the questions. Yeah, on homework 3. For 3.2. So I would just, this is about verifying the ODEs. And I would just use Mathematica. Yeah, I would just use Mathematica. Other questions? So what I would do, what I did was I would key in the formulas uh, for the functions that are given in the problem, and then ask Mathematica to calculate the derivatives and take those derivatives and plug them into the ODEs and see that the ODEs hold. I don't think you should expect Mathematica to solve the ODEs and give the formulas that are listed in the homework. I would take the formulas in the homework, write a code, write a like f of x is equal to whatever that expression is, and then have Mathematica write compute f prime of x, f double prime of x, f triple prime of x, however many you need of these, and f squared and all these things, plug them into the ODE system and see that the ODEs are satisfied. Yeah, other questions? Sherry, did you have a question too? Okay, then hope to see you guys tomorrow. If not, have a good spring break.